Okay, so this will be the final session on divide and conquer, right? So in the last session, we looked at two major algorithms. One is merge sort and another is quick sort. Okay, in this session, we will look at integer multiplication. So what is big about integer multiplication? We know how to multiply two integers, right? Suppose you have two integers. Let's assume positive integers. See, natural numbers, positive integers or natural numbers. And let's assume they are represented in the binary notation. So we have n bit natural number, right? A, and n bit natural number B. We want to multiply them. So we know one school algorithm, right? A simple algorithm that we learned in school. Bit by bit multiplication and adding them up. Okay, so like what was the idea there? Suppose we have say 27 times 31. What do we do? 1 times 7, 1 times 2, then 3 times 7. What do we have? 7, 2 carry, 3, 2 is 6, right? Then you have 8, then you get 7 and 3 here, 8 here, right? Something like this. Okay, you can use a very similar idea for a binary multiplication also. Suppose you have 101 times 11. Suppose these are binary numbers. That means only digits 0 and 1s are allowed. And how do we multiply these numbers? 1, if you have 1, repeat the entire first number. If you have 0, let's say you have this 1011, right? Then you have 1 here, repeat the entire number 101. You have 0 here, then you consider zeros everywhere, right? Then you have 1 here, repeat the number and add them up. So this is 1, this is 1, this is 1, this is 2, but we cannot represent 2, 0, 1 carry, right? 1, 1. So we know this school algorithm for multiplying integers. And if you look at this carefully, if there are n bits here, and if there are n bits here, how much will it take, right? The time it takes. So for every bit here, you need to copy everything, right? That is n bits. And similarly, for the next bit here, copy everything, n bits, n bits. So on, repeat this for n times, right? So if you add all these bits, you get n squared bits here in this range. So you need to do n squared computations. And of course, there will be carry and whatever, right? But you can write it as theta of n squared computation. So the school algorithm we know takes n squared amount of time to multiply two n bit binary numbers. I mean, you can generalize it saying, so if you have n digit integers, n digit, another integer, so to multiply again, theta of n squared number of one digit multiplication, right? The complexity is theta of n squared. So now we will try if we can reduce this further. So whatever, I mean, the algorithm we know for decades, right? We have been using for decades, but so this simple algorithm is not the most efficient algorithm. There are faster algorithms, right, to solve this problem. And probably we will look at one efficient algorithm based on divide and conquer, but there are many more Okay, there are many more. And we will see what can be the best algorithm for integer multiplication. See, that shows the power of divide and conquer. Right, let's start. So we are given two n-bit non-negative binary numbers. Assume there is no negative sign. We can always include it later, right? So it's unimportant. Okay, n-bit binary numbers. For simplicity, we will assume n is a power of 2. And why? Because we have to split and recursively split. So it is better if we have n, the size, as power of 2. I mean, we can generalize it for arbitrary n, just that there will be a lot more computations, and it gets a bit more difficult to, I mean, it gets a bit more difficult to analyze the code, right? But you can generalize it. But we will learn for n a power of 2 only. Okay. Now let's consider these two numbers, a n minus 1 to 0 and b n minus 1 to 0. So these are the two n-bit binary numbers. And we want to compute c 2n minus 1 to 0, right? And so this is your first number, this is your second. Okay, now let's think about it. Why did we write it as n minus 1 to 0? Why not 0 to n minus 1? I mean, all arrays, either we write it as 1 to n or 0 to n minus 1, right? But why did we write it as n minus 1 to 0? The reason is a binary number, say 1011, the first bit is the most significant bit. What do you mean by most significant bit? So consider this, 1011 is equal to, so 1 times 2 power 0 plus 1 times 2 power 1 plus 0 times 2 squared plus 1 times 2 cubed, right? So this one is the most significant bit. That means contributes the maximum value, right, is more important. This bit is more important than this bit. Okay, so this is the most significant bit, this is the least significant bit. So here we don't care about how it is stored in memory and all, because different computer architectures might have different ways to store it. I mean, that is unnecessary. So what the way we assume is that we are given an array, and in this array, I mean, you can consider this as an integer array or a Boolean array, whatever you want. Okay, so something like this, where the first bit here will represent the most significant bit. So that's why we write it as n minus 1, just for representation's sake, right? To understand, see, this is the n minus 1. See, so if this size is 4, right, you're multiplying this bit MSB with n minus 1 here, right? 4 minus 1, next 4 minus 2, 4 minus 3. That means 2 power 4 minus 3, 2 power 4 minus 4. So that's the reason we denote it like this. But when you're coding it, you can code it accordingly. Okay, but this will be easier to understand and do some computations, mathematical computations. Okay, so our aim is to multiply two n-bit binary numbers. Okay, so here is the subproblem. I mean, take one subarray of A, take one subarray of B, multiply, right? Multiply. What are we interested in? Multiplication of A n minus 1 to 0, B n minus 1 to 0. Okay, seems fine here. Here is the core idea. Okay, be attentive here. This is a very important idea. Now let's think about it. A times B, A multiplication B, A product B, right? So what we do is, we know A, so A is of size n is a power of 2, right? And B is of size n, and n is a power of 2. So what you do is split this binary number into two parts. The left half AL, right half AR. Similarly, the binary number B into two parts, left half BL, right half BR. Okay. Now what do? Let's expand it. You can write this as, see consider 1011. So 10 will be AL, 11 will be AR. I mean, we will see an example later, but just remember this. Okay, next. This can be written as AL times 2 power n by 2 plus AR. Why is that? I mean, think about 1011. 1011 can be written as 10 times 2 power. So what is the size of this? 4. So 4 by 2 plus 11. Do you agree with this? Do you agree with this concept?
Yes.
Okay. Now,
Actually,
yes, go ahead.
on the other hand, I think you probably can simply just 10 times 100, right? In this case, should be the same point.
10
But
times.
that's okay. Yeah, never mind. I think yeah, it's okay. Yeah.
Okay, so I mean, these are binary numbers, hence we are multiplying them with 2 power. Okay, so if they are say decimal numbers, you can multiply them with 10 power n by 2. Make sense? As
Yes.
these are binary numbers, we are multiplying them with 2 power. Okay, so if they are base 3 numbers, you can multiply them with 3 power n by 2. Okay, now you can expand ALAR like this and expand BR similarly. Now what do we do? So you know this formula, right? A plus B, C plus D, just expanding it. AC plus BC plus AD plus what else? BD. Just expand it. We will expand it here also. Okay, so 2 power n by 2, 2 power n by 2 is 2 power n. Multiply AL and BL. AL times BL. Okay, next, you can multiply AL and BR, AR and BL. So look at this. So take 2 power n by 2 out. Now it would be AL times BR plus AR times BL. You're taking 2 power n by 2 as a common factor, and plus remaining term AR times BR. You see what we are getting at, right? See, this is 2 power n. How do you multiply something by 2 power n? So what do you mean by 2 power n? Let's think about it. Multiplying by 2 power n. What do you mean by 2 power n? So consider 1, 1.
It just moved to the left by n bits.
Exactly. So if you want to multiply by 2 here, what do? You just add a 0 to the right side. If you want to multiply that number by say 4, I mean this number by 4, add 2 zeros on the right side. You can say you are just shifting that number, right? Those number of times. So any number, and say any binary number, say x, if you are multiplying with 2 power k, what is this? X, and then just write
K zeros.
k number of zeros. So multiplication with a power of 2 is dead simple, right? It's very simple here. You're just adding those many zeros. So This multiplication is very simple. This multiplication is very simple. So what is the remaining? Remain addition. Addition is simple. You know it is a linear scan. You have an array, you have another array. What is the time taken for adding? It's theta n. No big deal, right? But multiplication is taking more time. Now let's see. So this was our problem. What did we get? So we got another multiplication here, one multiplication here, another multiplication here, third multiplication here, fourth multiplication here. So all these are 4 subproblems. Make sense? Now we have successfully divided the problem into 4 subproblems. And how do we solve these subproblems? Recursively call them. Recursively call them. That's it. Recursively call these 4 subproblems, and in the base case, say multiplying two 1-bit numbers is easy, right? You can stop there if you want. That's it. So this is your recursive divide and conquer algorithm. A problem is split into 4 subproblems, right? Okay, next. So if you want to look at the diagram will look like this. Suppose this is the problem. You have AL, AR, BL, BR. This is one binary number. This is another binary number. And what do? The first step is the divide step. So dividing, what do we do? So like we showed all the computations there, right? We have to split one problem into 4 subproblems, and that split is by taking, see, ALBL, ALBR, ARBL, ARBR, right? So these are recursive calls. So we want to multiply them, right? We want to multiply them. So splitting A into 2 parts and splitting B into 2 parts and making sure that you create the input to 4 different function calls will constitute the divide step. So what is the conquer step? The conquer step is simple. Recursive calls. 4 recursive calls. That will be the conquer step. At the end, you will have the product for subproblem 1, the product for subproblem 2, 3, 4. Now what do? AL, BL, right? Let's go back. AL, BL times 2 power n. You multiply this with 2 power n, and you add these together and multiply them with 2 power n by 2. And you don't multiply anything with this, and then add all these sums. You get the final product of A and B. This will constitute your combine step. Divide step, conquer step, combine step. This is our divide and conquer algorithm for integer multiplication. So any questions here? So let's take a simple example.
Professor,
Yes.
I have a quick question.
Yes.
So do you mind to just go back to that slide? So here you see we see here we have 2 subproblems, right? AL, BL, AL, BR, AR, BL, AR, BR. My question here is, of course, maybe it has been AL appears twice, right? The P1 and P2. So if we recursively call, then should we make some reuse of AL, or separately called ALBL and ALBR for different subproblem.
Oh, good. Okay. So here, AL itself is not the subproblem. The subproblem is AL and BL to a function called multiplication, right?
Understood, yes.
So, I mean, we are still reusing that space AL. It's the same. So it's just giving pointer to that array, right? You don't need copy or anything like that.
Yes.
So you're reading from the same input space. You're not changing anything there.
Okay, I see.
Throughout the algorithm execution, you are not touching the A array. You are not touching the B array.
Okay, I understand. Yeah.
A new data structure C and adding everything to it. Okay. Okay, let's go back to this example. So 1100 times 1001. What do we do? So consider this 4-bit number as 2-bit, right? I mean, this is just for our understanding. This will be your AL, this will be your AR, left half, right half, left half, right half of B. Apply the same ideas. This is really 1 times 2 squared plus 0 0. 1 0 times 2 squared plus 0 1. Again, so expand it, you get something like this. So what you can do is, now this is your subproblem 1, subproblem 2, subproblem 3, subproblem 4. Can you tell me how do you solve, say, 1? How do you solve 1?
You do the same thing, right? So this in this case, AL is 1, AR is 1, BL is 1, BR is 0.
Right. So you do the same thing, right? So recursively 1 0, and then this will be written as 1 times 2 power 1 plus 1, right, times 1 times 2 power 1 plus 0. And expand it further, right? What do you get? 1 times 1, 2 power 2, right? And so on. And this is the base case, right? You can consider this as the base case and you can return a value here, right? Similarly, simplify everything. So try to apply this algorithm on this example completely till the base case. Okay.
Hi, Professor. I have a question.
Huh.
What if the number of bits is odd number?
Okay, good. So what we do is, suppose you are multiplying something like this: 0 1 0 1 times 1 0 0 1, say 1, something like this, right? What do you do? See, one simple way to solve this problem is, so there are 5 bits here, right? Make it as 8 bits. There are 3 bits here, right? Make it as 8 bits. Right? Make sure it is a power of 2. 8 bits, 8 bits. Now apply the algorithm. The complexity will not change. The theoretical complexity will remain the same. Right? See, so you are appending the initial bits with zeros. That will not change the value because you know, right? 1 1 is same as 0 1 1. It is same as 0 0 1 1. Same as 0 0 0 1 1. So you can always append zeros at the starting point. If you append zeros after the ending point, it means you're multiplying by 2 power number of zeros. Okay. So this is called padding. So you can pad at the front to make sure it is a power of 2. and recursively solve. Now let's go to the pseudocode. So the pseudocode is something like this: product of one subarray of A, one subarray of B, H2L, H2L. So H is the most significant bit. And let's assume that this is a power of 2. I mean, we are assuming that it is a power of 2. It's easier that way, right? Okay, so what do? What's the base case? If H is equal to L, right, 1 bit times 1 bit. It's very simple. Return 1 bit times 1 bit, whatever the answer is. If it has more than 1 bit, what do? Find the midpoint, right? So H plus L by 2. It would be probably easier if it is a power of 2. You can easily solve it. So H plus L by 2. Then what do? You can split this A subarray into 2 subarrays, AL and AR, high to mid, mid plus 1 to low, high to mid, mid plus 1 to low, for B also. Okay, so here you're just defining what is AL, what is B, okay, AL, AR, BL, BR. Okay, next what do? So this is dividing, right? Divide step. Concourse step. Find the products as we saw in the diagram, right? AL, BL, AL, BR, AR, BL, AR, BR. So we have 4 different products: P1, P2, P3, P4. You can run them in parallel because we are not changing these A arrays and B arrays. And anyway, we are returning all the products as a return value, right? We are not changing anything. So these are essentially independent functions, independent tasks. If they are independent tasks, we can run them in parallel. Okay, so once we have 4 products, what do? So AL, BL times 2 power n, right? So P1 times 2 power n, P2, P3, P2 plus P3 times 2 power n by 2, right? Plus P4. That was your original answer, right? From the core idea and example. So this was the formula we used. This is the combined step. Combined step. Third step, combined step. Right? So divide step, and then concourse step, combined step. Right? This is your pseudocode. Now let's analyze this pseudocode. What happens? Suppose this is T of n, n-bit binary number. So what do we do here? There are 4 calls, 4 T of n by 2. Each is of size n by 2, right? 4 T of n by 2. Now you can say there are 2 input arrays, right? Don't we need to do anything? Shouldn't we consider 2 parameters? No. Though we have 2 arrays, the parameter is only 1. This is also n-sized array. This is also n-sized array. So T of n. So this would be 4 T of n by 2. Now think about what happens here. You're multiplying by 2 power n, right? So 2 power n means you need to shift by n bits. So you can say plus theta n. That means you need to at least do something like a scan, linear scan, right? So you have to do n computations. You cannot do better than that. And adding anyway takes n time, right? This takes n time, this takes n time, adding takes n time. So overall, you can write it as plus theta n. What about divide step? Divide step, no big deal. So this is theta 1, right? Combined step is complicated here, right? Combined step takes a lot of time, I mean, for processing, but it is same as the number of bits here. So your time complexity will be 4t of n by 2 plus theta n. Solve it, you get it as n squared. Okay, what about depth? 4 function calls in parallel, so it is just d of n by 2. Depth is theta n. Now look at this. How did you improve the running time? This is same running time as our school algorithm. We used a complicated idea of divide and conquer, and still we are getting the same running time. Then what's the use of divide and conquer? Of course, here the use is we can parallelize it. Okay, parallelizing will be helpful. And you can also say that this has cache, a very good cache locality, right? It uses cache really well. So this divide and conquer algorithm is better than the school algorithm, you see. Okay, it's definitely better than the school algorithm. One is in this parallel running time, it's way better, and in cache complexity. What about work? We are not reducing the total number of computations at all. But our first aim is to reduce the computations, not increasing parallelism or cache complexity. It's the work. This is our top priority. So can we reduce work? Yes, there is a way to reduce work, reduce the total number of computations. Okay, and we will analyze it after this idea. Now think about it. So here is a simple toy problem. So what is this problem? You have two complex numbers, a plus ib and c plus id, and you want to multiply them. Okay, multiplication is trivial. AC minus BD plus I times BC plus AD. This is the multiplication of two complex numbers. Right? We studied complex numbers in probably school, right? Okay, there are 4 multiplications required for multiplying two complex numbers. But there is a better way. We can multiply two complex numbers using only 3 multiplications. What is the idea? So consider x is this, y is this, z as this. Then the real part, this is the real part, and this is the imaginary part, right? Then the real part is this, y minus x, and imaginary part is z minus x minus y. Verify this. So if you use this idea, we can multiply two complex numbers using only 3 multiplications, not 4, just 3 multiplications. And this is not just the only idea, right? There are many more. This is another solution. This is another solution. All these solutions use only 3 multiplications and not 4 multiplications. Okay, why are we learning this toy problem when we are, working on a very serious problem, integer multiplication? Because this toy problem gives a very beautiful idea, right? That is the backbone of one of the most important algorithms in computer science. Okay, so that is this algorithm, right? Karatsuba's algorithm that we will see. Right. Let's start from this. This Karatsuba algorithm, when it came in 1962, I think, right, around 1962, it shook the world of mathematics. The reason is everyone thought you cannot do better than theta of n squared number of multiplications, right, or complexity for integer multiplication. But what Karatsuba showed is that, no, you can asymptotically do better than that. You can reduce the computation significantly, right? That shook the world of mathematics. And it is based on this toy problem, reducing 4 multiplications to 3 multiplications. Right? Simple idea, right? Now let's see. A times B. Use a similar approach. AL, AR, BL, BR. And we also saw this. We know how to do this. And we expanded it. That uses 4 multiplications, right? We have already seen this, 4 multiplications. So now this is like our toy problem that had 4 multiplications. We will reduce it to 3. Let's see how. You can write it as AL BL times 2 power n, AR times BR. So we will keep this multiplication. This multiplication. We will keep this multiplication. Okay, let me highlight this one. This multiplication, first multiplication. And we will have the second multiplication. And then we will have the third multiplication. This is our third multiplication. Problem solved. So this is our first multiplication, product P1, product P2, product P3. And then what about this? This is same as P1. We can reuse it. We don't need to multiply again. What about this? This is same as P2. So reuse it. We don't need to multiply again. Right? If you verify the answers, this computation will be same as this computation. This term will be same as this term. This value is same as this value. Why? Okay, we understand the first term and last term, they match. What about middle term? Okay, let's try it out. If we make sure this middle term is same as this, we are done, right? Let's see. AL BL plus AR BL plus AL BR plus AR BR minus we have this, right? AL BL minus AR BR. This is what we have. AL BL cancels out. AR BR cancels out. Whatever we are left with is AR BL AL BR. That is same as this expression, isn't it? So the expression here matches with the expression here, but we are using only 3 multiplications. Of course, this is reused, this is reused. So we are not really computing it, we are reusing it. So only 3 multiplications we are recursively calling. What do you mean by 3 multiplications here? That means there are only 3 subproblems. There are only 3 child functions. Look at the mapping. We reduced 4 multiplications to 3 multiplications in a toy problem. If we repeatedly apply that, we are reducing 4 multiplications to 3 multiplications. That implies we are reducing 4 child functions to 3 child functions, or 4 subproblems to 3 subproblems. So this simple idea, right? We laugh at this. If somebody reduces by one multiplication or one addition, we laugh at it, saying, what is so big deal here? But repeatedly applying the same thing can give us asymptotically better algorithm, faster algorithms than the world has seen. So this one simple idea, right? Reducing 4 multiplications to 3 multiplications led to the discovery of a new algorithm of integer multiplication, which is asymptotically better. That means the number of computations is way polynomially better than the school algorithm, which everyone thought is the best algorithm, right? Till 1962, people thought, okay, you cannot improve it, that's the best algorithm. But look at this beauty, right? Okay, now let's look at the diagram. AL, AR, BL, BR, and what do we have? We have 3 subproblems only, AL times BL, and this and this. We get the products. Now what do? We multiply product 1 with 2 power n, right, as given before. We don't look at this, ALBL times 2 power n, right? And then ARBR times nothing. So we just add whatever it's there here. But P2, let's look at P2. What do we do with P2? P2 minus P1 minus P3. So what we do is P2 minus P1 minus P3. So finally, how do we combine? We return, look at this, P1 times 2 power n plus P2 minus P1 minus P3 times 2 power n by 2 plus P3. Right? This is the combined step. Make sense? So let's take an example, 1100 times 1001. So split all this as before. The first 3 steps we have already seen. No need to, worry about this, right? Now let's look at how do we reduce the number of multiplications by 1. So this remains the same. The last term remains the same. The middle term, what do? 1, 1 plus 0, 0. So what was this? Remember this, AL plus AR times BL plus BR. AL plus AR, that is 1, 1 plus 0, 0 times 1, 0 plus 0, 1. That's what is written. Minus this product minus this product. I mean, we are not recursing on this, right? Once we find this value, we will reuse it here. Once we find this value, we will reuse it here. Make sense? Okay. Then now look at the divide and conquer algorithm here, right? See, it's very similar as before. The base case is same. In the recursion case, you find mid, you split A into AL and AR, you split B into BL and BR, and you find the 3 products. How do you find the 3 products? AL times BL, AL plus AR times BL plus BR, AR times BR. And you see that these 3 products, computation of these 3 products are in parallel, right? One is not dependent on another because the input arrays are same. You are not changing the input arrays. You can read infinite number of times from an input array, right? So multiple reads is totally possible. You can have multiple threads reading from something. That won't violate anything. But if multiple threads are writing to a common variable or location, that is problematic. So if it is multiple reading, simultaneous reading, that's no problem at all, right? So you can run these tasks in parallel. And now what do? You have P1, P2, P3. As I said before, the combined step will be P1 times 2 power n, that is AL times BL times 2 power n, plus P2 minus P1 minus P3. And we have seen the computation before, why this is true, right? Times 2 power n by 2 plus P3. We don't multiply anything to P3. So as before, step 1, theta 1. And so, okay, we will come back to this. And what about this? 2 power n is still the same, theta n. You're not changing anything here. So divide step, same. Conquer step, theta n. You're not changing this. What is the change then? The change is instead of 4n, n by 2, it's 3 times n by 2. Instead of 4 calls, you have 3 calls. So you successfully reduce the number of function calls by 1. Okay, what happens to the result? If you just reduce the number of calls by 1, apply the master theorem, right? What do you get? N power log 3 base 2. Everything else remains the same. Depth is the same, right? Depth is the same. Depth is not changing. This combined step is not changing. Base case, anything, all those are not changing. N by 2, still the same. Instead of 4, you have 3 here. Automatically, the number of computations decreases a lot polynomially. You had n power 2. In that place, you have n power log 3 base 2. Can you tell me what is n power log, say log 3 base 2 quickly?
N to the power 1.6 roughly.
Right. N power 1.69 or something like that, right? Approximately.
It's 477 divided by 301, something like that.
Okay,
so it's a little bit less than 1.6, I think.
Oh, less than, okay. So let's write it as something like O of.
Yeah.
See, you should never write theta of n power 1.6. Do you know why? Because, see, this is a real number. Log 3 base 2 is a real number. That means it has infinite decimal digits. You can only write theta if you write those infinite decimal digits or with dot, 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 right? If you are rounding it off, that rounded value is either greater than the real number or smaller than the real number. If it is greater or smaller than the real number, how can it be theta? Either it has to be O or it has to be omega, right? If you're taking a greater value, you can use O. If you're taking a smaller value than this real number, you can add omega. But omega is uninteresting. You want to find the worst case, not the minimum case or something like that, right? So, yeah, better keep it like this. Theta of n power log 3 base 2. So if you see it, it's, yeah, I mean, probably less than n power 1.6, something like that. That is amazing, right? So n squared to n power 1.6, or in that order, is an amazing improvement. It's a polynomial time improvement. Though it is 0.4, but what if n is trillion, right? As n keeps increasing, I mean, people have used all these algorithms for very large numbers, right? As of very big sizes, because big data is all about big sizes, right? So when n increases a lot, the power of this difference, right, will be can be easily seen, right? So anyway, so this is the asymptotic improvement, polynomial time improvement over existing trivial school algorithm, right? Which was inefficient. Okay, let's recall. First, we had the school-based algorithm. You can write a simple double for loop or something like that to write the code for that school algorithm in say 10 to 15 lines of code, right? So that took n squared time. Then we came up with a divide and conquer algorithm and used a lot of ideas there, but still we were getting the work as n squared. Of course, the depth was really good. So it's a good parallel algorithm and it had cache complexity. However, we could not reduce computations. But what we did is we used a beautiful idea of reducing the number of multiplications from 4 to 3 and used it to reduce the number of child functions or subproblems by 1. That automatically reduced the total number of computations polynomially. So we had 2 divide and conquer algorithms. Remember, the first one did not improve work. The second one, Karat-Subba's algorithm, this is called Karat-Subba's algorithm, improved work. So just because you used a divide and conquer, it does not mean you will always get improved work. Think about array sum divide and conquer. You need not get improved work or asymptotic improvement in computations, right? Or just because you used a divide and conquer technique and did not get improved work, it does not mean there is no other way to apply the divide and conquer in a better way, right? So there are 2 take-home lessons here. One is, if you apply divide and conquer, it does not mean that you will always get improved computations, right? The complexity improves over the existing standard. That's the first take home. Second take home is, just because you applied a divide and conquer in a bad way, there is no other way to apply it to get improved work, right? So there are 2 take home lessons. Okay, so with this, we are done with integer multiplication. Let's move to matrix multiplication. So like integer multiplication, okay, so consider the multiplication of 2 objects, A times B. If A and B are numbers, you call them, say, integer multiplication. If they are integers, you call them integer multiplication. If they are matrices, you call them matrix multiplication. If they are polynomials, you call them polynomial multiplication. So this multiplication concept itself is beautiful and used in a lot of fields, right? Integer multiplication is a different concept. It has different set of algorithms. Matrix multiplication is defined in a different way. It's not element by element multiplication, right? It's slightly complicated. So there are a different class of algorithms here for matrix multiplication. And think about polynomial multiplication. Suppose you have a 10th degree polynomial, multiply it with, say, 15th degree polynomial. How do you find the solutions? Right? That's a different problem. Polynomial multiplication. So for different problems, variants of these multiplication, we have different sets of algorithms. And all these are based on divide and conquer. Very good algorithms are based on divide and conquer, right? For all these integer multiplication, matrix multiplication, and polynomial multiplication. Anyway, so before we start matrix multiplication, I just want to make one more point. See, though we got n power log 3 base 2, right? This is not the best algorithm for integer multiplication. In fact, very recently, maybe, I don't know, 2 years ago or something like that, French researchers came up with an n log n time integer multiplication algorithm. Okay, I mean, before that, it was n log n, log n, something like that. But currently, the best bound, and it is probably the optimal bound. You cannot do, I'm not sure if they have shown a lower bound, you cannot do better than n log n, but maybe it is n log n, but I don't know if there, anybody has proved a lower bound. But the current best algorithm we know for integer multiplication is n log n, theta n log n. Look at the beauty of this. Where is n squared and where is n log n? When n is large, n log n is very, very, very near to n. Right? So there is a huge gap, right? From n squared, we reduce it to almost n log n. So if you say something like this, right, we can multiply two integers of say n bits or n digits and say n log n, people will not believe it. I mean, a school algorithm seems like the best algorithm, right? If anybody, works on it for a few minutes, it seems impossible that you can do better. But see, there are so many algorithms. The best is n log n, the current best. But we don't know if we can go below that. Okay. So what is this matrix multiplication problem? So here we will majorly focus on square matrix multiplication. Okay. So we are given two square matrices, A and B. A and B. We want to compute the product of A and B. And how do you define this matrix product? Now consider this product, C of ij cell, highlighted here, right? How do you compute this? So here it is in the second row, third column, right? So what you do is you take the second row in A and third column in B, and then multiply each integer. So 5 times 4 plus 8 times 6 plus 3 times 8 plus 8 times 5, that will give you 132, right? So similarly, how do you compute C of I comma j? So take the ith row of A, take the jth column of B, and do this element-wise multiplication and add them up. You get C of I comma j cell. Okay, so mathematically you can define it like this. So if A and B are n cross n sized matrices, though it is generalized for arbitrary m cross n, but here we will keep this simple problem, right? Square matrix multiplication. We can always generalize it later with a lot more details. So we want to find the matrix product C from A and B. A times B is equal to C. And how do you define a cell of C? C of ij is defined as sigma, because you want to add, right? Finally, add all these values. Sigma aik times bkj for all k. Okay, now let's think about it. What are we doing? So you are computing C of I comma j. Take the ith row of A and jth column of B. Ith row is I comma dash, and jth column of B is dash comma j. And you do an element wise, the first element of A, right, with the first element of B in that row and column respectively, right? A of I1, B of 1j, A of I2, B of 2j, A of I3, B of 3j, so on. Multiply all these pairs, add them up, right? That's the definition of matrix product. Okay. Now we want to multiply two matrices. Right? Okay. Let's go to the core idea. Okay. So C is equal to A times B. You know that in divide and conquer, we have to divide the input. If it is an array, you just split it in the middle. If it is a matrix, split it into quadrants, right? You have 4 quadrants. What if you're dealing with a 3D matrix? Split it into octants. What if you're dealing with d-dimensional matrix? Split it into orthants. How many orthants will be there? If you're working with d dimensions, there would be 2 power d. So here it is 2d, so you have 2 power 4 quadrants. For a matrix, d is equal to 1. Sorry, for an array, d is equal to 1, you have 2 power 1, 2. For 2d, you have 4. For 3D matrix, you have 8. For 4D matrix, you have 16, and so on. Again, what about polynomial? Polynomial also can be represented as an array. You can split that array in the middle. So see, everywhere, wherever you are dealing with arrays or matrices, the core idea is the same. The initial step of divide is the same. Split the array or split the matrix. So into 4 equal quadrants, right? A11, A12, A21, A22, B11, 12, B21, B22. Similarly, C11, C12, C21, C22. Okay. Now, how do you compute C11? We have 4 quadrants of C. We have to compute each of these quadrants using each of these quadrants of A and each of these quadrants of B. So how do we compute C11? Recursively, the idea is, now think about this A as a 2 cross 2 matrix, B as 2 cross 2 matrix, C as 2 cross 2 matrix. Now, can you tell me how do you multiply 2 cross 2 matrices? How do you compute C11? Take the first row of A, take the first column of B, multiply, right? So A11 times B11 plus A12 times B21, right? That's your C11. Okay, now let's try one more. How do you compute A21? Sorry. C21. How do you compute C21? C21. So the second row here, so, right? If we assume that this is a 2 cross 2 matrix, this is the second row, and take the first column of B here. What do you get? A21, B11 plus A22, B21. Right? That's what is written here, right? A21, B11, A22, B21. So on. Okay, now you don't need to assume it's a 2 cross 2 matrix. Assume it is, say, 2 power k plus 1 cross 2 power k plus 1 matrix. What I mean to say is, okay, so entire C is 2 power k plus 1 times 2 power k plus 1 matrix. What about this will? So this will be 2 power k, 2 power k size, right? So you can recursively compute it. It's no longer one value. If this is a matrix, recursively compute it. Recursively compute A11 times B11. Recursively compute A12 times B21. Recursively compute each of these products. So how many products do you have? How many products do you have?
You have 8.
You have 8 products. That means you have 8 child functions. You have 8 subproblems. Okay, so plus, I mean, you have plus everywhere, right? You can split it like this. So it's same as this matrix plus this matrix. But each of these matrices will have 1 product each. So one problem, A times B was solved using 8 subproblems, and those subproblems are already given here. 8 subproblems. A11 times B11, A12 times B21, so on. And you have addition. Addition is no big deal, right? It's easy, linear scan, right? So this is the core idea. That means, suppose you have 2 input matrices of size n cross n. For simplicity, assume n is a power of 2. A11, A12, A21, A22, so on. Splitting is easy, right? It's just, you know, kind of constant time. Now, second step is conquer step. You have 8 subproblems, 8 child functions. Recursively call them, recursively compute them. And you get a lot of these products, say C11 dash, C11 double dash. And you add them up here, right? Remember, we had to add them. See, this is one subproblem. This is one subproblem. You compute them. Assume that this is C11 dash. Assume that this is C11 double dash. If you add them, you get actual C1, right? That's what we are doing here. So add each of these solutions to the subproblems, you get a quadrant of C. And all these quadrants of C itself is C. You have 4 different quadrants, that itself is C. So divide step is simple. Conquer step is recursive calls. Combine step, you need to combine it in this way, right? You cannot add arbitrary solutions. You have to add the solutions to these 2 subproblems only, right? Then these 2 subproblems only, then these 2 subproblems only, right? This is your divide and conquer algorithm. Okay, so if you look at another diagrammatic way, so another diagram, it's like this. So mm of A is the input, B is the input, C is the output. The output is shown in red because you need to write on that region, right? It's dangerous. You cannot run them in parallel. But blue is input. You can read unlimited number of times from blue. That is the input. So what you do is, so the idea is something like this, right? Split it into 4 quadrants. Then C11 is A11, B11, right? Then C11 is, okay, along with this, what you do is you add, right? A11, so it's this, right? A11 and B11 was added to C11. Now what do you have? A12 and B, this is 21, B21, A12, A12, B21. Again, you add it to C1. You can see, right, this is the, partial solution. And when you add this also, it's the complete solution, right? Similarly, but look at this, as you are writing on C11 using two different tasks, you cannot run these two in parallel. See, you are writing on C11, you are writing on C11 again. You cannot run these two in parallel, right? But what about the other function calls? You are writing on C12 here. It has nothing to do with C11. So you can run that in parallel, and all other quadrants in parallel. So these four function calls can be run in parallel and synchronize here, and then again run these four calls with four different tasks, run them in parallel. At this point, you will have the complete solution in C. And how would you solve this particular problem? Again, recursively, right? How would you solve this particular subproblem? Again, you split it into four quadrants, repeat, like the way you have here. Makes sense, right? So, okay. Your algorithm will look like this. The pseudocode will look like this. A, B, you multiply them and add it to C. And these are of sizes n cross n. So look at this. In the base case, if n is equal to 1, then C is equal to C plus, whatever. You can initialize C with all zeros, right? Beforehand, you can initialize all C with zeros and then call this function. C is equal to C plus A times B. If it is one cell, it's dead easy, right? You can just multiply and add it. Okay, what is the recursion case? So you have 8 child functions, right? 8 child functions, first 4 and then next 4. So first 4 in parallel and then next 4. The first 4 function calls are writing onto 4 different quadrants of C, right? 4 different quadrants of C. That means they are independent tasks. Hence, you can run them in parallel. And then again, call the remaining 8 tasks, right? Or child functions in parallel, right? That's your solution. See, once you understand the core idea, right? How we get these 8 child functions or 8 subproblems, then it becomes relatively easy. Now let's analyze the complexity. Complexity is there are 8 child functions. Each subproblem is of size n by 2 cross n by 2, right? So here you are dealing with n cross n matrices, but you don't need to write it as n squared or whatever. If it is n cross n, you can write it using one parameter only, right? See, the second dimension is dependent on the first dimension, length. So you can just write it as n. So when you reduce this subproblem, this will be n by 2 cross n by 2, right? So it is of size n by 2. That means the parameter is n by 2. That means the size is n by 2 cross n by 2. There are 8 such functions, 8 child nodes, 8 subproblems. So 8 times t of n by 2 plus theta 1. Why is it theta 1? Why is it theta 1? So think about it. Splitting is nothing, right? Splitting A into A11, A12 is nothing. It's like finding the mid and something like that, right? So that is theta 1 time. finding the mid position. And then splitting is nothing. You are adding everything into the respective quadrants of C. You don't need to manipulate it in some way, scan it, or right, nothing is required here. So it's theta 1. Okay, so theta 1. If you compute it, you get n cube. N cube is no better. And depth, you have 2 here. Why? Because you have, look at this, 2 parallel keywords, 2 parallel steps. This is 1 parallel step, 1 parallel step. This is the another parallel step. So 2 steps, hence 2 d of n by 2. If you solve this using master theorem, it's theta n. And work is theta of n cubed. Theta of n cubed. See, we applied a complicated idea here. We could have easily coded it using 3 for loops, right? For. Right? You have, say, I, J, K. For this is the I loop, this is the J loop, this is the K loop. And you could have computed C of Ij is whatever. It was so easy to write it in a 3 for loop, maybe 4 or 5 lines. In under 5 lines, you could have coded it and got n cube solution. But we applied complicated ideas and we still got n cube solution. I mean, the computations is still n cube. We did not reduce this. But of course, this is a parallel algorithm. Depth is really good. Parallelism is really high. And cache complexity is wonderful. Right? So we still have to improve the work. Again, we will use similar ideas as in this toy problem. We have to reduce the number of multiplications from 4 to 3, right? We used it here. We will do a very similar idea. I mean, not similar, but getting inspired from it. But instead of 8 recursive calls, we will do it in only 7 recursive calls. Okay. So I will directly go to the pseudocode. I don't need you to understand this each and every line or anything, but remember the complexities here. Okay. And at a very high level, what it is trying to do. Of course, remembering all these calls, what it does is too difficult because this is a very highly complicated algorithm. Okay, now let's take a look at this pseudocode. What are we trying to do? There are 7 different subproblems here. See, instead of 8, we have 7 different subproblems. A1 times B1 gives you product 1. A2 times B2 gives you product 2, and so on up till 7. A1 is computed like this. A2 is computed like this. How? Using the quadrants of A. Similarly, B1 is computed using the quadrants of B. B2 is computed using the quadrants of B. So we know how to compute A1 to 7, given these formulas, and B1 to 7, given these formulas. So this is the divide step. Divide step. This is the conquer step. We recursively take the product of A of I and B of I to get P of I for I in the range 1 to 7. So there are 7 subproblems, not 8. And once we have these 7 subproblems, what do? we combine these different products to get the first quadrant of C and combine a couple of products to get the second quadrant of C, similarly third and fourth. And how do you get all these weird formulas? I mean, how can one think about these kinds of formulas? See, look at, which quadrants of A and B to consider, which products to consider and add to get quadrants of C. See, it takes at least one complete lecture to analyze right, the core ideas behind this. It's a highly complicated algorithm. So at this step, right, we don't want to go over all these details, how, why, how do you show that it is correct and so on. But just remember that there are 7 child functions, right? 7 subproblems, and you combine it in this way so that you can reduce the time complexity to n power log 7 base 2. See, when you reduce this number by 1, the work asymptotically reduces to n power log 7 base 2, which is better than n cube. So you will see that for n cube, you can write it as n power log 8 base 2, right? For n cube. You reduced from this to this, right? That's a polynomial time improvement. Okay, so just remember this, how do you compute this complexity and depth complexity and so on. You don't need to remember all the details of Strasson's algorithm, but know the core idea. The core idea is in reducing the number of subproblems. That is by reducing the number of multiplications itself, right? And so using the same core idea that was used in Karatsuba algorithm and Strasson's algorithm, see, they came up with groundbreaking ideas and algorithms, right, which shook the world of mathematics and computer science. Okay, so we will stop here, right? In the next session, we will explore a new topic.